Okay, welcome back to this course on polymer chemistry. In the last lecture, we were discussing about gel permeation chromatography and then about mass spectroscopy for determining polymer molecular weights. And with that, we came to end of the discussion of how to determine polymer molecular weight. Today, we will move to a different topic, which is structural analysis of polymers by spectroscopic method. Now, we have in the beginning of this lecture series, we knew or we found out how to synthesize polymers by different process, and then in next set of lectures we found out how to characterize the polymers in solution, including the how to determine the molecular weight of the polymers. Now, we will know whether the polymer, what is the polymers we have made. So, in this chemical structure analysis, we will be basically discussing mainly the spectroscopic techniques by which we will be analyzing the chemical structures, including the microstructures of polymer molecules, and out of this listed spectroscopic methods, we will mainly discuss the NMR techniques to use of the NMR techniques mainly, and we will briefly mention about UV visible and IR spectroscopy, and we have discussed mass spectroscopy in the last class. So, it is very critical when we make that we know how to make these polymers and what is the molecular weight of the polymers we made. Now, obviously, we need to know whether we have made the right polymer. We maybe have something particular in mind in terms of chemical structures, in terms of end groups of the polymer, and if we are making copolymer, then the microstructures of copolymers, the composition, the series, the sequence of the monomers by which the copolymer is made. So, all these are important. So, we must know before going to further to know the property or to determine the property of these polymers which we made, we must know what is actually the chemical structure of the polymers. So, it is very important or crucial to know identify the repeat units. We may have used a particular monomer, but whether that monomer exists in the same form as a repeat unit, we need to find out what is the end group of that polymer, what is the molecular microstructure in terms of homopolymer. For example, the tacticity, whether it is syntactic, atactic or isotactic, and then chemical compositions of a copolymer, the mole fraction of the repeat unit, the sequence of the different repeat units in a copolymer. And spectroscopy is the most powerful method which we can utilize to get the structural analysis done. Now, what we will do in this lecture, we briefly talk about the interaction of electromagnetic radiation, the basis of spectroscopy, interaction of electromagnetic radiation with matters, in this case polymers. This is, all of us know, the electromagnetic radiation, and this is the increasing wavelength. So, this is the left hand side is increasing frequency, which makes this increasing energy, and this is a short wavelength, it can penetrate atom. So, we study X-ray diffraction using X-rays here. Next is little higher wavelength or little less energy is the UV visible spectrum, where we mainly probe the electronic transitions of a molecules, and then using IR infrared spectra we can probe the molecular vibration, and finally with the radio frequency radiation we can use this radio frequency in NMR technique to know the chemical structure of the polymer molecules. So, basically the matter can interact 2-3 ways with the radiation. It can absorb, and intensity, when it absorb, it intensity can change from I0 to OI. So, you can plot transmission or the absorbance versus wavelength, and to find out at which wavelength it is absorbing maximum and what is the criteria and so on. In terms of emission spectra, light, when we shine a light in the sample, it can absorb and then it can emit maybe in the same wavelength or a different wavelength, and with the help of detector we can get the intensity of this emitted radiation, and the different types of emission spectra we can use: fluorescence, emissions from excited electron singlet states, phosphorescence, emission from excited electronic triplet states. The other type of interaction is scattering and optical rotation. The sample might change the rotational polarization of the sample, causing change in optical rotation of the light. In a basically very simple manner, how these equipments are done: light source is there is a light source, and there is a frequency selector which basically select a single frequency, or you can have the entire light in that particular region of interest pass through this, and it hits the sample, and then you can detect the transmitted light or the emitted light using detectors, and then you get the information about the sample from absorption spectra or emission spectra, or a scattering, like Raman scattering. Now, come to UV visible spectroscopy. Just talk about in this course, we are not going to go in very details about these spectroscopic techniques, because these are very basic techniques. What I will just mention a basic few basic like points, and then tell you what is the application of this particular spectroscopy in terms of polymer characterization. So, in terms of UV visible, basics of UV visible spectra, it is basically electronic transitions from the highest occupied molecular orbital to the lowest unoccupied molecular orbital, HOMO and LEMO. If there are non-bonding electrons molecular orbital, sometimes if the non-bonding molecular orbitals are the highest orbitals, occupied orbital, then electronic transition may happen from a non-bonding molecular orbital to lowest unoccupied molecular orbital. So, for molecules which have only sigma orbital, mainly sigma orbital, then the HOMO-LEMO transition happen between sigma and sigma star, which is of quite high energy and not having very practical interest. If there is a pi bond in the compound or the molecule, and especially if the pi bond, there are many pi bonds which are pi orbitals or pi bonds which are conjugated, then the pi transitions are of like UV visible range, and the more conjugation, more it goes to visible range and the higher wavelength, and this is having very practical significance, which help us to find out the group functional groups or the conjugation present in the molecule. And non-bonding non-bonding orbital to pi stars are very weak absorption, which happens in this region 200 nanometer to 400 nanometers. So, which basically implies presence of non-bonding electrons in the compound. So, how this UV spectroscopy is applied in polymer science, in characterization of polymers? Basically, it is like how the UV spectroscopy is applied to for the small molecules. For example, it helps in detection of particular chromophores, which mean light absorbing groups present in the molecules. And if we have groups like acrylic acids or methylic acid or styrenics which have a strong absorption, then this type of polymers actually help us in detecting the trace amount of residual monomers. If there is monomers are present, then it will give a strong UV signal, UV visible absorption signal for that monomers, and obviously the UV visible absorption spectra for the monomers or the peaks for the monomers and the polymers will be different. So, we can follow the monomer peaks and to find out the conversion during the polymerization. If in a copolymer, if one of the polymers the two monomers, they have a different UV spectra, UV visible spectra, then we can follow their, we can isolate the polymer after the polymerization is over from the polymerization medium, then we can get the composition simply by studying the UV visible spectra of the polymers. For that, of course, we need to know the absorption behavior of the individual homopolymers, like in this case polybutadiene and polystyrene. If we know the individual UV visible spectra, absorption spectra for polybutadiene and polystyrene homopolymer, then from there we can easily get the composition of polybutadiene co-styrene. We can use as we discussed in case of GPC technique, we can use UV visible detector to find out the molar mass distribution, and we can get the with the help of UV visible spectra we can get the GPC molar mass distribution curve. And of course, as the pi bonds, the conjugation pi, the more the conjugation, the higher is the absorption. So, by following the conjugate sequence of pi bonds, we can follow the conversion of polyacrylated fiber into carbon fibers. So, these are some of the examples of UV visible spectroscopy in polymers. And next we will move, there are a few more examples like dyes. Sometimes we use dyes in polymers for coloration. So, we can analyze the amount of dyes present. We can also analyze the specific additives which are where the additives are UV visible active. So, basically we can use this sort of we can use the UV visible spectroscopy for this sort of use in polymer science. So, next move to the IR spectroscopy, and as I mentioned, we will just mention the basic things about this spectroscopy and then move to the application in polymer science. Now, as we all know that IR spectroscopy are mainly used in functional group determination, and it is basically a transition between different vibrational states of a molecules, and this energy gap between the vibrational states such that it resonate with the electromagnetic radiation about having wavelength of 1 micron to 50 micron. So, typically we run a IR spectra from say 4000 centimeter inverse to 400 centimeter inverse, and for a non-linear molecules there are, for n atom, if the molecule have n atom, the number of vibrations is 3n minus 6. So, for you can imagine for a polymer molecules which have large number of atoms, so many number of vibrations is possible, and each have individual absorption in that IR region. So, the IR spectra of polymers have lot of these absorption bands, and it is impossible, it is very difficult to assign for a particular reason or particular vibration for all the absorption peaks in IR spectra for a polymer. But obviously that does not restrict us to use IR's technique to polymer characterization, because the functional groups present in a molecule, it may be in the polymer as well, they do not change the absorption in IR, whether it is present in a small molecule or a polymer large polymer molecule. So, what happened if we found those particular vibration bands or IR peaks, then we know or we can assure the presence of those particular functional groups in the polymer, which help us to characterize the polymer molecules. So, as you know that there are different types of vibrations possible, like stretching and bending, and this is important that interaction of matter with IR radiation occurs only when these vibrations produces a change in dipole moment. So, it happens. So, the IR spectra, IR absorption happen only for the vibrations or bending vibrations for the polar bonds. And this is the chart or cartoon gives typically the range where this IR absorption happen for a particular bond vibrations like OH, NH, they comes around in this range, and C triple bond in, then comes this CO double bond comes around here. So, this is basically a guideline for where the peaks come corresponding to functional group. Polar bonds show strong absorption at higher frequency generally, and intensity, shape and the position of this IR bands typically used to identify the type of absorption. This is example of FTIR spectra for this particular polymer, and this is a particular bond for NH stretching, this is for CH stretching, and so on. So, this is the IR spectra for is not very special in the sense that it's same as the use of IR in detecting the chemical structure of polymer molecules is similar to the application of IR for small organic molecules. Is basically help us to determine the presence of functional groups in polymer molecules. So, what we will do, we will go next to NMR spectroscopy, and now as this all of you may be knowing that NMR is about transition between magnetic energy levels. So, in a few thumb rules, like if the molecules is NMR or a nuclei is NMR active, if the spin number I is not equal to 0, if it is 0 then it is not NMR active, and there are few general thumb rules. If the atomic mass and atomic number are both even, then I is 0, so they are NMR inactive. If the atomic mass is even, atomic number is odd, then its I is whole integer, and all nuclei having odd atomic mass, they have a half integers. So, like proton, carbon 13, they all have I value of half. Now, they can in general rule of thumb is that if the I has some value n, then 2n plus 1 is the number of states they can basically, they have the number of states levels, energy levels, magnetic energy levels. So, if I have for a proton I is half, so it can have 2 into half plus 1, which makes it 2 different energy levels, which is basically we call this is minus half and plus half. So, what happened in terms of pictorial representation, this for a proton molecule, these spins are randomly oriented when there is no external magnetic field. Now, so in the absence of any external magnetic field, these are randomly oriented. Now, if there is external magnetic field applied to the molecule, then they can align in two different ways. They can align with the external magnetic field, or they can align against the magnetic field. Now, these two states are energetically different. Obviously, this is having higher energy than this. So, this is having lower energy and this is half energy, higher energy. So, in presence of external magnetic field, the nuclei can have two different energy state, and now if we apply a nuclear magnetic radiation whose energy is in this cap, in this range, then some of the nuclei from this lower energy level can move to the higher energy level by absorbing the nuclear magnetic radiation. With increasing external energy, external magnetic field, the energy between the two state increases, and with increasing in the difference between the two energy state, the population is in the lower state, which is ground state, becomes more and more compared to the higher states. So, if you have higher magnetic field, there will be more number of molecules or nuclei in the lower state than higher state. So, when you have a nuclear magnetic radiation coming, more number of nuclei can move to the higher state, causing absorption. So, with increasing in external field, the intensity of absorption always go up, and the sensitivity of the instrument or the measurements goes up. Now, this is we know that in a molecule not every nuclei experience a same amount of external field. Basically, in surrounding a nucleus there are electron clouds which basically shields some of the external magnetic field applied, and the more the shielding, more is the effective, less is the effective external magnetic field the nuclei experience. So, with the change in the chemical environment around a nuclei, the effective magnetic field the nuclei experience will change, and hence the radiation, the lambda at which it absorbs. So, you can, if you compare in a standard different groups, like in case we are talking about hydrogen atom, proton. Now, these protons will have different chemical environment, so they will have experience a different external magnetic field. So, their resonance energy will be different. Now, though they are very small, they can be resolved, and so they can be put in a scale. So, from the NMR spectra we can get idea about the chemical environment of the proton here. So, the more shielded it has higher delta H, lower delta H value, and if it is deshielded then it is having a higher delta H value. Now, this probably are known to you, so I am not spending too much time on this. There are this may be also known, but let me complete. When you observe a NMR spectra, what does it mean? The number of signals or peaks we see in a NMR spectra, it means that is the number of equivalent groups of protons or carbon. If you are talking about carbon 13 spectra, NMR spectra, then we are talking about that many number of equivalent groups of protons present in the molecules. The chemical shift or the delta H value will give the idea of what type of chemical environment, so what type of group, what type of proton or carbon they are. Intensity of the signals will be proportional to the number of protons or carbons contributing to the signal. So, obviously, if the signal from 2 protons will be double than the signal from 1 proton. The signals can have a splitting which gives the idea about the neighbors, and the line shape, whether it is a sharp or it is a broad, it gives idea about the interaction of the solvents. More sophisticated NMR techniques like relaxation time, NOV, they gives idea or information about dynamics of a molecule. So, in case of polymer, if we apply relaxation time, if we get the relaxation time, then we can get the information about polymer dynamics, and NOV gives the information about special arrangement of atoms. Now, this is interesting in terms of how we apply NMR spectroscopy for polymer science. The discussion about last few minutes about NMR spectroscopy is general, which is applied to any organic chemistry or any other science, any other course, but this is specific to polymer science or polymer chemistry, where we apply NMR for identifying the chemical structure, composition and microstructure. Obviously, the first one is the identification of polymers and functional group. This is same as the way we identify the organic molecules from NMR spectra and functional groups. So, this is new, not new, from the chemical shift and the intensity and the coupling values, we can get information about the polymer and the functional groups. And obviously, we know which are the monomers we have used for making the polymers. So, we have a priori some idea about the NMR spectra. So, basically this confirms that the polymerization has taken place. Obviously, the NMR spectra for the monomer will be different than it, especially different than the polymers. For example, if you are talking about vinyl, any vinyl molecules, so with polymerization the double bond will be absent. So, with progress with the following the intensity of the double bonds and protons in that CC double bond, we can follow the polymerization process. We will just give you example in a minute to elaborate more on that. Composition, if you are talking about say copolymer between A and B, we will be able to find out using NMR how much A and how much B in the final polymer. What is the type of chain structure, whether it is a random, whether it is alternating, or it is a block nature of the copolymer, that is also able to, we will be able to find out using NMR spectra. For a polymer, we can get idea about the tacticity, and also if we apply some chemical reaction or if we can find out the N group, we can also get a information about the N group present in the polymer. Now, let us discuss few examples. Now, this is a NMR spectra, proton NMR spectra for PMMA. This is one example, one PMMA, not every PMMA made in the lab or in the plant should look like this, but it is one example, one PMMA made in the lab, and this is the proton spectra of that particular PMMA sample. Now, this obviously this shows that this is for this O methoxy group, and this peaks are for alpha methyl group, this one, and these 2 protons are given by here. Okay. Now, this alpha, the protons from alpha methyl groups, they will have different chemical shift depending upon the special arrangement of the next carbon. For example, if the next carbon here, this particular one, let me draw this and explain a little bit here. Now, here it can have 2 special arrangement. One, it can have like CH3 and so in this case, we, as we discussed in terms of copolymerization, this is one arrangement, and you can have same here, and now this is a arrangement which is alternating here, and these 2 carbon have alternating stereochemistry. So, this is a triad, this is a TOR triad, and their arrangement is RR, racemic, and this case it is, if I talk about this thing, they will be different. So, all these 3 arrangement RR, MR and MM, they will have different chemical shift, and from this particular sample it is seen that if you go back and look at the NMR spectra in the computer screen, this RR is the maximum compared to the other two signal. So, if you compare the area under this curve, which is nothing but the intensity of those signal, it comes about approximately 65%, and this is 32% and this is 3%, which shows that this synthesized PMMA is predominantly a syn diatactic PMMA. If you have this MM groups maximum, then you would have the isotactic PMMA maximum. Now, this is the spectra for a copolymer of MMA and styrene. So, this is a copolymer of styrene and MMA, methyl methacrylate. If you look at the struct proton NMR of this particular compound, these 3 proton peaks are for the 5 aromatic hydrogen of the styrene moieties. So, these 1, 2, 3, 4, 5, there are 5 hydrogens for this 5 hydrogen aromatic. These three peaks 1, 2, 3, they are for this O-methoxy protons in this O-methoxy group, and they also not same depending upon whether they are syndactic or heterotactic or a isotactic, their chemical shift value will differ. And this is for your alpha CH3 of the PMMA group, and these peaks are these 3 carbon atom from polystyrene backbone and these 2 hydrogen from the PMMA background. So, what does this spectra help us? This spectra can give us idea about the composition. For example, if we talk about this 5 hydrogen, so if I just consider that you have one styrene molecule, one styrenic unit rather in the polymer backbone. So, it has 5 hydrogen. Now, the integration corresponding to this is 1.00. This is 1.00 for 5 hydrogens. So, 1 hydrogen means, this means 1 hydrogen corresponds to 0.2 integration. So, if you consider now this alpha CH3, this is from 3 proton for the MMA moieties. Now, the integration for this is 2.57. So, if 1 hydrogen corresponds to 0.2, 2.57 integration will corresponds to 12.85. If you multiply this by 5, you will get 12.85. So, this is the number of protons. Now, each MMA moiety will have 3 hydrogen. So, how many MMA moieties? If you divide 12.85 by 3, which is 4.28, around 4.28 moieties of MMA. So, in this spectra corresponds to 1 styrenic moiety and near about 4.28 MMA moieties, which means the composition percentage of MMA is 4.28, 1 plus 4.28 into 100, which gives around 81%. Okay. So, from this is one example that using the proton NMR spectra, you can actually get the information about the composition of the copolymer. Now, obviously, to do this exercise, you have to identify peaks which are correspondence to particularly one moiety. For example, this one we had for the styrenic moiety and this one for this PMMA moiety. And also we need to be very careful about that we have to run many scans in the NMR as possible to make this spectra more quantitative. The lesser the number of scan, the error, the more will be error in the composition. So, from this example where we can find out the composition of the copolymer and what is the type of copolymer. In this case, it can be seen it is more of a co-syndactic copolymer. Next example is we made a block copolymer of polytertiary butyl acrylate, and polystyrene using leaving radical polymerization raft. So, this is the monomer First, this is this reaction scheme. This is the monomer tertiary butyl acrylate, and it was reacted with this. It is undergone radical polymerization by EIBN in presence of heat, in presence of this chain transfer agent, and you have this first macro wrapped agent or first block. So, this is a block of tertiary butyl acrylate. There should be two ends here to represent this is the polymeric or oligomeric unit. Now, from this what we can do, we can get the molecular weight of the first block, and then when we react with another monomer, in this case styrene, then we can make a block of polymer. This is also present this side. So, we have, this is the way we synthesized a block of polymer of tertiary butyl acrylate and polystyrene. So, from this, the NMR structure of this, we can get the molecular weight of the first block, and from the NMR of proton NMR of this second, we can get the composition of polystyrene and polytertiary butyl acrylate, and obviously from that we can get the block length of the second block as well. How? This is the example, this is the proton NMR spectra for the first block, which is the tertiary block, the block of tertiary butyl acrylate. Now, these peaks correspond to these 4 aromatic protons. So, you cannot see it properly, but it comes around total. So, 4 hydrogen comes around 1. So, this corresponds to 4 hydrogen of these 4 aromatic protons. Now, this 0.53, this is 0.53. This 0.53 is from the 3 hydrogen, these 3 hydrogen of the polybutyl acrylate block. So, that corresponds to 3 hydrogens from polybutyl acrylate block. Now, if 4 hydrogen corresponds to 0.11, then how many hydrogen it should corresponds to? 0.11 divided by 4 multiplied by 0.53. So, this is the number of protons for that particular signal. So, number of tertiary butyl acrylate moieties in the first block, is by 4 divided by 3. Four hydrogen corresponds to 0.21. So, 1 hydrogen corresponds to, there may be a mistake I am making here. So, this could be okay, fine. So, what I maybe the calculation may be something maybe little different, but what you understand, what you know, that if you consider these are from these 4 aromatic protons, and these from these 3 protons from tertiary butyl acrylate moieties, then obviously you can find out from the intensity ratios how many protons are there, and from that how many tertiary butyl acrylate groups, and from that you can get the molecular weight of the first block. Simple. Now look at these peaks. These are for these 3 hydrogen present here in the monomer 1, 2 and 3. 1, 2, 3, 3 peaks for the 3 olefinic hydrogen present in the monomers. So if you have the ratio, from the ratio of the peaks of this corresponds to 3 protons for the monomer, and this corresponds to the 3 protons of the polymer. So from this ratio you can find out what is the conversion of monomer into polymer. So obviously with more and more time the reaction goes, this will come down and these peaks will go up as the molecular weight also goes up. So this means that not only using proton NMR spectra we can get the molecular weight of the first polymer, but also we can monitor the this is a spectra from a crude sample. So we can monitor the amount of conversion of monomer into polymer with time. So basically we can do a kinetic study of the polymerization process. Now once you isolate the pure monomer first block and then add to the and then reacted with the styrene molecule, it get this block copolymer. Obviously from this ratio, now this is a longer chain. So obviously you can ignore these 4 aromatic protons compared to the number of aromatic protons present in the styrene. So you can assume that all the aromatic proton peaks are from these 5 styrenic moieties, whereas these particular peaks are from the 3 hydrogens from tertiary butyl acrylate moiety and styrenic moiety. So from the ratio of these 2 you can now find out what is the molar ratio of the styrenic moiety and the tertiary butyl acrylate moiety, and you already know the molecular weight of the tertiary butyl moiety. So obviously now you can find out the molecular weight of the styrene moiety or the styrene block as well. So with this is example where we showed that using proton NMR you can get the molecular weight, and obviously you need a N group type which is specific peak for N group. Here it was a styrenic peak which were available for determination. So we not only we can find out the molecular weight, we can find out the conversion from monomer to polymer, and also if we add the second monomer to form a block, then we can get the information about the composition of the block as well as the length of the molecular weight of the individual blocks. So this is example where we showed that the proton NMR can be very useful to get the information about polymer microstructure. Now let us give few examples where we talk about carbon 13 NMR can be used to quantify and identify the polymers. Let us take example of polycarbonate. We know we have seen during our first few lectures, this is the way we make polycarbonate. Bisphenol A is reacted with a carbonate source. So this is the structure of polycarbonate. Now from a carbon 13 NMR spectra we can assign each and individual carbons in this polycarbonate, and this peak is special A. This carbon from the carbonate peak is special because with help of this spectra we can find out the composition of a copolymer which we will show as example in the next slide. So, this is example of a co-polycarbonate which is consists of BPA and other other compound TMBPA time we are talking about. Now, this carbonate peak, if we call this A and this A, so this particular carbonate is from, if the copolymer have two bisphenol A group making a carbonate linkage, which we can get information from the bisphenol A polycarbonate homopolymer. So, we can assign this peak A from polycarbonate BPA homopolymer. Similarly, if we can make a homopolymer of this particular monomer, then we can know what is the chemical shift for this carbon C13 peak for this particular carbonate. So, when you have copolymer, from the ratio of these three peaks, we know the amount of this type of carbonate present in the system. So, if you, these are the example for this copolymer made from two different processes. So, in case of a, say if we are having a 50-50 mixture of A and C, these are the two monomer, and you can have ACO, you can have ACOOC, let us put it B, make it, and you can have, so three types of carbonate possible. This one, this is 3, 1, 2, 3. Now, this peak we can find out from a homopolycarbonate of A, this one from homopolycarbonate B. So, the third peak would be from this. Now, from the ratio of the intensity of these three, we can, like in this NMR spectra, we can find out what is the ratio of this particular type of present in the copolymer. So, if we go back and look at this screen, computer screen, this is the, in this process of polycarbonate, this peak say corresponds to AA, this block, this carbonate, and this is corresponding to this particular carbonate, and this is for the this particular group. So, which makes that this is present in double amount corresponding to this individual. So, if you start with a 50-50 mixture, obviously if it is random, it is from a random copolymer, you will get this as a 25%, this is 25% and this is 25% plus 25%, 50%. So, if it is forming A and B is forming a completely random statistical copolymer, then the percentage of these three carbonate peaks would be 25%, 50% and 20%. That is exactly this example of 50-50 copolymer. This is where exactly happens. So, this is from this curve, this NMR spectra, we can say that in this process we get a statistical random copolymer, whereas in this case you can see that the tendency of formation AA block, AA type carbonate and CC type carbonate is much higher than the AC or CA type carbonate, which means the polycarbonate here is more of a blocky nature than this. This is a more random work. So if at least with this type of NMR's analysis, we can clearly say that whether a copolymer is a random copolymer or a block type copolymer. So, if you from this chart we can this is a statistical way of presenting the expected value of mole fraction of the type of linkages in the copolymer with the mole fraction. Like in this case, if we have a 50-50 composition of A and B, so our composition was mole percent 0.5, then this A block would be 25%, BB block would be 25%, and this alternating AB block will be 50%. So, this is for a purely statistical random copolymer, which is the case for in this case. So, this is how we can using NMR we can get the information about the randomness and the blockiness in this. So, with this we stop for this lecture, and we will start next topic in the next lecture.